Let's see now the coupling part. And to understand the coupling part, we need to simplify it a little bit. So let's go to here. So for the myosin head, since all of the work would be that the myosin head is going to the actin binding site, so all of the focus will be on the myosin head. And for the myosin head um, to understand it better, I need you to think of the myosin head as the spring, like the one in the picture. This is like you can find it in any regular pen. So it's like the spring. The default position, let's put it in this way. The default position of the head is that it is standing. Standing. Exactly as the spring. So if you leave the head alone, it will stand and fit inside the actin groove. And that is why we need the tropomyosin when we don't need the muscle contraction to happen, because the tropomyosin will physically block the head from going inside. But now, since we are talking about the contraction, we need the head to go inside. So when the head is standing, it will fit and go inside. So this is the first position for the head. The second position, let's call it a flat. What does it mean? It means that the head would go all the way down. The head would go all the way down, really away from the actin. So this is the second position. The third position will be in between the standing or the flat, which let's call it bend or bended. Actually, they are calling it the cocked position, but let's call it bended for simplicity. So bended would be something like this. Okay? And as you could see with the pictures about the spring, it's exactly like you have the spring and I can bend it all the way, or I can, like, to make it flat, or I can bend it like halfway. Now, these three positions, the myosin head is moving between them. So the myosin head in a different, or like rephrase the sentence, the myosin head is moving between these three positions, from standing to flat, and from flat to the cocked position or to the bended position. And then from the bended, it will go back to the standing, and so on. So from standing to bend to flat, and then from flat to bended, then from bended to standing. Oh, that's three, and so on. And it will keep repeating itself. So let's see now how this actual contraction is happening. So we will have my beautiful drawing of the actin. Okay. And we can actually start from any position, like either from standing or flat or the cocked position. It doesn't matter, as long as we understand it is the cycle, we are going to end up in the same position, so it doesn't matter. So I will start with the standing, maybe it's easier. So as you can see, the myosin is fitted inside the actin. Okay, and technically this is the standing position. Now there is something they call it cross bridge, meaning that the myosin is connected to the actin. Now to break this cross bridge, we need energy. In other words, in order to move the head away, we need ATP. Exactly as the spring. If I want to bend the spring all of the way, I need to use some of my force, some of my like I have to put some force on the spring to bend it all the way down, as you can see in the picture or in the video on the screen. So here we will use an ATP molecule. So there will be an ATP molecule. Or actually, let's draw it in a different picture, in a different drawing, so you would understand what's happening. So this will be like sequences. So this is the head, the actin, the myosin. Okay, now there will be an ATP molecule comes and sit on the myosin head. Now think of this as a force. So because of this force, the myosin head will move to the next position, which is flat. So the myosin head will move to the flat position, which is the position number 2. Okay, position number 2. This was position number 1. This is position number 2. The actin heads are still here. Okay, the actin heads are still here. Now ATP, this ATP is one of the markers of ATP, one of the characteristics of ATP, that is it's quickly broken down. So quickly broken down. If you remember from chapter 3, ATP, when it's broken down, it will convert to ADP, adenosine diphosphate, and plus inorganic phosphate, plus energy. Okay, this energy is what going to move or bend the myosin head. Exactly, I am moving, as I'm moving my finger, or giving some energy, giving some power, or using some force to bend the spring all the way down. So immediately after this bending, ATP will converted to ATP, to ADP, and it will release the inorganic phosphate. But during this transition, like here it is ATP, I will draw it in a third drawing. During this transition, actually we will have less force. Think of it as we will have less force on the myosin head. Because as you can see exactly on the spring, so when I'm pressing the spring all the way down, it will become flat. But if I reduced my force over the spring, it will raise up a little bit. Yet it's not completely standing. And this is exactly what happened here. Because ATP converted to ADP, and inorganic phosphate, this was like released plus the energy. Okay, so now this is the third position, the bending or the cocked position. But this won't last forever. At a certain point, the ADP is going to be released off myosin head. Which will cause the head to become standing again. Now, This movement from here, like I want to use like a dashed color. There is no dashed color here. Okay, like this movement from here to here happens so fast as a snip, exactly as you can see on when I'm releasing my finger off the spring. It will snip, it will snatch, it will like kind of jump. This jump is happening with force, and when the head is moving in this direction, it will go actually, my bad drawing, it will go inside the groove of the actin and it will hit it. So the head would go inside the groove and hit the actin. And because of this hit, actin would be pushed forward. Okay? The actin will be pushed forward. Then the same cycle will be repeated. ATB, again, the same cycle will be repeated. ATB would come and bind, make it to the flat. Then ATB will be broken to ADB and inorganic phosphate. And once it's released from the myosin head, the myosin head will jump, will snap up, and it will hit the actin. And this will push the actin forward. However, every time it's snapping into the head, it will move the actins forward. So like we started, this is 1, 2, 3. If you see, like we started here with 1 and we ended up with 2. So on the second round, the head would snap number 3. So this is on the second cycle. And on the third cycle, the head would snap the 4th actin. And so on. So because, and as you can going to see it in the video, in the other video with the animation, because of this repetitive movement of the head snapping up, we are going to see the we are going to see the movement of the myosin, the actin, moving toward the M line, or actually the Z discs moving closer to each other, which is the contraction. So the contraction is happening when we have this cross bridge between the myosin and the actin, and because when these actin heads are snapping up or down, they are hitting these actins and they are causing them to move forward like this. So this will bring the entire Z discs close to each other, and that is the contraction. Okay? And this model of contraction is called sliding filament. Why? Because the actin is sliding along or in parallel to the myosin. Okay? That is the sliding filament model. And technically here you have the same steps that I explained. Now here they are putting them in different wording, but it is the same thing. Okay, I just tried to make it simpler. I will stop the video here, and I need you to go over it again and try to absorb it. Try to absorb the entire process, the excitation, contraction, coupling. This is like a summary, okay, of the entire process from the action potential all the way to the muscle contraction. Technically, when the muscle fiber contracts, the entire muscle is going to contract. Okay, so I'll stop here, and when we come back, we will talk about a few other things in this chapter.